Last Tuesday, and then continue with the notes, and then we're going to program it in MATLAB. Then I'll probably take a little break. Then I want to show you a little more detailed analysis of some of the stuff, and we'll probably end up doing the code either starting it today or finishing whatever on Tuesday. Okay. So we have up here is the differential equation that solves conduction and convection. And we non-dimensionalized it. It's typically what they do. We had these boundary conditions, all right? And I'm hoping by now that you understand where the differential equations come from. All they are some of the forces written in different terms. Boundary conditions limit the boundaries, okay? Initial conditions are time-based. So the FEM approach, or FEA, doesn't matter, whatever, the way they do this is they get it into a weighted integral form. So they take the differential equation, they multiply it by some function, in this case we said v, and then you integrate. That is the basic steps for this type of process. Okay, there's a whole bunch of math and reasons why. We can spend another 2 weeks on that. I kind of want to sprinkle some concepts into you so you kind of understand the basics. And if you ever get into more FEM concepts, this is important to know. So what we're going to do today later on is we're going to define what t is and what v is. Those can be any functions you want. This is a cubic functions. We're going to do cubic today. You could do quadratic, you could do linear, you could do whatever, okay? Well, basically what you're doing is you're approximating that differential equation with a function, with actually a couple functions. And that's how you solve the FEM, okay? So what we had to do here from the blue to orange is when we multiply this function, we split these terms up. We have 1, 2, 3 terms. And we try to break them down into smaller, easier terms to look at. So this one, though, we had to do integration by parts. And we ended up getting this term over here. And then what I ended up doing here in red is just rearranging. And we ended up with this orange from last Tuesday. Okay? We have the left, we have the right. And the left side has t and also v in both of these spots. But on the right, it basically has v. And these over here with the lines indicate boundary conditions. Okay? So on the right, it's just v really as the main function. Everything else are numbers. So you have a bilinear function on the left and you have a linear function on the right. So now there's a few more lines that we're going to write, talk about some things, and then we're going to kind of show you how we break this apart and then program this. Okay? So what we need to do first is, and there's math behind this, but don't worry too much about it, is you have to define, draw, let's pick a color. Let's go with green. Change in variables. Okay? And this becomes important because we're doing some boundary conditions and there's some rules about it. Don't worry too much about why, just, okay, this is what we're doing. All right? Say that again? This is a T star. So the T star, T hat, we're going to replace with T star plus 5/3. And that 5/3 comes from the boundary condition. And so let's go ahead and plug that into the orange equation. And I'm going to plug some of these boundary conditions in. So v of 1 minus t, oops, parenthesis, t star at 1 plus 5/3. And then we're going to subtract v of 0 d t star plus 5/3 over dx hat. I don't know why that parenthesis is so big. It doesn't have to be.
What's T star?
It's just a, we're replacing t hat with t star plus 5/3. It's just a new variable that includes the boundary conditions. There's a complicated reason why we do that. I don't want to get into that. It's due to the boundary conditions. There's an issue with boundary conditions, and you have to change this. Yep. So this term right here, oh, I didn't want that color, I wanted red, is actually the boundary condition, which was that, which was t star over dx star at 1. Okay? That's just the boundary condition on the right side of the beam. If you remember, we're looking at like this. This is 0, this is 1. So the boundary condition over here is the derivative, which is 1 minus t hat. And that was given in the problem. This boundary condition over here on the right is the boundary condition at basically x hat of 0. Okay? And we're going to get to that in a second. So we did this. If we look at this term right here, what is usually the derivative of a constant? 0. So the this d of 5/3 over dx hat, if we multiply it, that would actually be 0. So we don't even have to worry about those terms anymore. Okay? So the 5/3 of that term would go. You'd have to keep this because there's no derivative. Same thing over here. And what we're going to get is this. This is the last equation before I show you how we break this apart. Okay? So we're going to now look at this a little bit more. We're going to pick some functions. I'm going to show you how we break them apart. Okay? So as long as you understand that if we have a differential equation, if we multiply by a function, we integrate, we break things down, we're going to get a bilinear function and a linear function. Okay? As long as you kind of understand that now, when you ever get to this in the future, you'll kind of understand what's going on. Just a few things to note. Boundary conditions, there's actually three types. There's Dirichlet, there's Newman, and mixed. So give me one type of boundary condition that you've seen before, and I'll throw it where it is. That's initial conditions, not time. Okay, there you are. There's one where you assign one variable to another. So Dirichlet could be this. You assign a temperature at x of 0 to be 2. Okay? What about Newman? What do you think a Newman is? Boundary condition. Okay. Or a calc 1, the derivative. So like negative t dx could be q. Probably doing this in heat transfer, maybe, I hope. And what do you think mixed is? When you have a derivative and numbers.
Is that the Nusselt number?
Where? Way up top? Yeah, Nusselt number, yep. Yeah, when you start dealing with convection and conduction, depends on if it's free or forced, right? You have to have the Nusselt number. Okay. Questions so far? All right. Now, what we're going to do is we're going to pick t to be this. A of I, x of I. We're going to do a cubic. A1 x hat plus A2 x hat squared plus A3 x hat cubed. All right. What's the derivative of that? So we'll do cubic. So someone tell me the derivative of that function with respect to x hat. Almost. I think you missed a 2 right here.
Oh, 2, yeah.
And then 3a3x hat squared. Okay? Why do we need to know the derivative? Because if you go back to this red equation right here, there's a derivative, right? And actually, you can call these, sorry, these are t stars. Okay, now we need to pick a function for v, and let's do cubic, but different constants. And then we need to know the derivative of v with respect to x. So b1 plus 2b2 x hat plus 3b3 x hat squared. So really, we're going to use these 4 functions. We're going to plug those in to that red equation. Then we're going to do some linear algebra to show you how we extract these. Okay? All right. Okay, so go up here. So we're going to look at just the bilinear function first, just that term. So we're going to plug in those variables that we just defined. So this could be a little bit long, so bear with me. So b of v comma t equals integration 0 to 1. And the first term was what? dv dx hat in the red equation? Is that what we did? Yep. So that's b1 plus 2b2 x hat plus 3b3 x hat squared. And put a parenthesis at the beginning. Parenthesis, we've got to multiply it by dt star over dx hat. So a1 plus 2a2 x hat plus 3a3 x hat squared. Plus, what we got next? The Nussel number times what? V or T. Did we do T or T star or did we do V? Okay, so I'll do A1 x hat plus A2 x hat squared plus A3 x hat cubed. And then multiplied by B1 x hat plus B2 x hat squared plus B3 x hat cubed. Close parenthesis, and we've got that term. So let me just zoom out a little bit. Pretty crazy, right? I mean, you could take any differential equation, do everything that we just did above. Multiply by a function, integrate, separate the parts. You may have to do integration by parts if there's two derivatives. Identify a new equation for your variable with your boundary condition. Plug that back in. Do more algebra. Define a linear, quadratic, cubic, fifth order, fourth order, doesn't matter. Okay? And then you plug these back in. Then we have to do what? Plus v times t star t. So if we go back up here, this term we got to do, right? What is it evaluated at? 1. So we just plug 1 in for x. Pat. So I'm going to put it down here. Plus b1 plus b2 plus b3 times a1 plus a2 plus a3. We're getting there. We're getting there. Now, we're going to do linear algebra. We're going to put B1, B2, B3. And then this is going to be a big matrix here. And I won't do it all. I'll do some of it. So let me put the first one in. It's going to be integration of 1 plus the Nussel number x hat squared times dx hat plus 1. That's basically saying take B1 and A1 out. So what you do is you multiply those top things out, and you basically can factor out that term. Okay? The next term is going to be integration of 2x hat plus nu x hat cubed dx hat plus 1. And this is factoring out b1, a2. And hopefully I have enough room. If I have to erase, I can erase. And I'll put the last one in purple. This would be 3x hat squared plus nu x cubed to the to the fourth dx hat plus 1. And this one is factoring out b1 a3. And let me finish this and multiply by a1, a2, a3. So, just to help you where we got these, let's do this in, I don't know how yellow, let's do red. If we multiply b1 times a1, right, that first term, and we factor out a b1 and an a1, what are we left with? A 1. Does that make sense? Okay? So that's where this 1 comes from right here. Over here, we multiply nu times this term times that term. We factor out the a1 and the b1. What are we left with? Nu and x hat squared. Then down here, we multiply this by that. We had just 1. So you see how we get those terms? We do b1, a1, and then this term is b1, a2, and so forth. So what you're going to have is this is going to be like more values here, 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 and here. Okay? This is going to be a 3 by 3 matrix. So what I just showed you, we've kind of done with direct formulation, right? We built a matrix. Okay? This matrix is your big stiffness matrix, if you want to think of it that way. Okay? So we just did, and I don't want to write all those. I think I might have a cheat sheet later on for this that I made copies for. We got to do the linear function, then we can program. So the linear function was nu times v 1 minus 5/3 dx hat plus v 1 minus 5/3 at x hat equals 1. So we're going to plug in what v was. So nu times b1 x hat plus b2 x hat squared plus b3 x hat cubed. What's that? I just want to show you this. It's a lot of math. FEM is basically math on super steroids. But I wanted to show you this. We're not going to spend like more than 3 days total on this stuff because I wanted to show you if you ever get into the situation, you have an idea of how this stuff works. So you don't feel completely overwhelmed if someone's trying to talk about it. Like I'm kind of preparing you for when you hear about noise, you know what noise they're talking about. If students know what I'm talking about that went on the trip. There's frequency noise, and then there's hearing protection noise. You want to know the difference. Okay?
Okay, I see what you're trying to do that.
Yeah. That's why I want to go through. That's why sometimes I go through some of this stuff, because you have an idea when someone says something. Okay? What's that? Yeah. That is the whole matrix, right? Because you just factored out B1, B2, and B3. Okay, just a couple more lines. So this is what we have. So the underneath the blue, the purple there, it's just the bilinear function equals the linear function. But what I'm calling K is our stiffness that we made, 3 by 3. This F, is just this matrix that we just made. Then the next line down, I just factored out the B1, B2, and B3. And then what is one solution to that equation right there? Anybody want to guess? An easy 0. What do you mean by that? B1, B2, and B3 are all 0, right? That is our linear function constants. Well, we know that we don't want that, right? So we take Ka minus F, and we set that equal to 0. Tell me how to find A now in linear algebra terms. You've done it on one homework, you've done it on direct formulation twice. A equals K to the minus 1 times F. Remember that? And what is A? A is your coefficients to what? T star. And you got to remember that T hat then is T star plus 5/3. So it all hopefully comes back to hopefully making a little bit more sense. And there's a few things I want to review and tell you why we do some of this stuff. Okay, then we can program it. What's that? Yeah, remember when I said we have to make a new variable? We had t hat, it was t star plus 5/3. Yep. T hat was the non-dimensional differential equation. And t star is based on the boundary conditions to help with our solution. So every t that you have, Devin, should be t star or t hat except for t stars because it's the non-dimensional. So this was, hold on, I'll show you. This was the differential equation that we were trying to solve. And you actually solved this in one of the homework problems. I think, or we did it together in class or something. So just to recap and let you know why some of this is. If you have a differential equation, which we're solving right here, and we're solving that based on a beam, okay, where we have convection and conduction. This is 0 and this is 1. We want to do it in non-dimensional terms. In order to do FEM on this, okay, where basically, if you remember, what is the basic definition of FEM? Like, we split these up, right? We cut them up. So that's what x hat. We're going to do, x hat we're going to define as distances between here. Okay? So we break these up, and at every point, basically, we're going to solve that differential equation. We know that conduction equals convection kind of thing. So the rules are, you have to multiply the differential equation by a function and then integrate. Break those down, apply your boundary conditions, and then you do linear algebra to get basically these equations, that matrix, that one, and this 3 by 3. Then you basically do this one. You invert your K matrix multiplied by F to find your coefficients for this function. And then you can then finally figure out what t hat is along those points. Okay? That's the basics of FEM right here. Okay? And you've done some of this before. So let's go ahead now and start programming. So if you don't have a computer, you can probably grab that one or whatever you want. So let me, everyone got the notes? Okay. So what I'm going to do is probably do MATLAB maybe on here. And I won't get it to work, so actually you want to work on this one then? Sure. Because I don't have Sims, but that's okay. I don't feel like switching my recording. So go ahead, start a new script, do clear all, close all, CLC, and then we're going to define X Nussel number, and we'll do some fun stuff. Fun stuff. FEM stuff. And an element. Yes, they're just that one. You pick. Don't worry about that because your final project is stuff for your capstone. Okay. Pick one. There's two things in there. Pick one. Same with you, Alex. You could either do the CD or you could do the. There's a 2-story building. It's harmonic on. Doesn't matter which one you do. That's just going to be pick one. And then Paul, your final project's that one, since you're not in capstone. So both of those. Yep, that's the last homework, and that's your project. Yep. Now, I haven't done the project. Ryan Vollmer did the CD, got it to work. So the CD works. I don't know the final project, but it's basically something that you're pulling in and out. Okay, so let's start writing some code. All right, can you see that okay? X, we're going to define X. 0, 0.01 to 1. So really this is X hat. I don't feel like putting underscore hat. Nussel number we'll define as 100. And the analytical, X is 2 divided by 3 times EXP times negative SQRT, Nussel number, times X plus 1. Figure 1, plot X versus TX, comma B, line width 2. And then go ahead and run that to make sure it works. Hoping to have a completely different setup. Wow. We're going to move all the computers over here to the corner. Now, it's 3 to 5 computers over there. And we have 2 laptops. Like 7 computers here. Yeah, sorry for graduating. We'll be back. So for propulsions, we're going to be doing a lot of MATLAB. Line width should be a single quote here. Sorry. Yep. What's that? Yeah, you need to practice on your typing if you haven't figured that out yet. Yeah. And if you want to try it, try doing actually I only give you the top 3, right? So if we do Sims X, what is K11 in our matrix? See if you can do K11, K12, and K13. I already gave you those. Let's see if you can convert those to programming code. When is it? It's going to be Monday, Wednesday, Friday, Monday, Tuesday. Can't do it? Do workflow. I'm going to record them. The plan is to go through concepts. I'll give you a homework. You're going to do homework. We'll go through the homework. Prop design, triple jet, triple props, probably circle and rockets. I do, yes. I have to get it. Or is it motion? It might be, it should be. Yeah, I think it should be. Did you mail that in? Oh. You got it there?
Yeah, I didn't want to.
Oh, okay, you're doing X hat. Okay, yeah, fine. What are we doing? Right where? How do you type?
Not well. I can put it here, but then I just start typing random.
You need to get Mario. They have a typewriting thing that Mario with money. It actually has you type numbers and letters and all why it teaches typing. So you got it working? That's the analytical solution. Yep. So at 0, the temperature, T hat is 1.65. The non-dimensional number is. How do you find T then? Remember?
Just regular T?
Yeah.
Don't you iterate that?
T hat was T over T infinity, which is 300. So you just multiply by 300.
Yeah.
I hear beeps. Do you?
Me.
Yeah, you should get a curve that does this. That's what you should get. But this is t hat, right? And this is x hat. Work now, right? Oh, this. Alright, did you get it, Ryan? Oh, you can't run it, yeah, with those. Oh, can you figure those out yet? Sure. Dante, how you doing? You get it? Okay. Oh, your x must be too small. Did you choose your dx? The 0.01? See how it's choppy? Yeah. You didn't get it. Why did you go to 100? No. It's non-dimensional. Go 0 to 1. There you go. Now, this is non-dimensional temperature, T hat. That's non-dimensional x hat. In order to find the actual temperature, it's multiplied by T hat. Okay, looks like everyone was pretty much there. Wesley, I know Paul's behind a little bit.
Yeah, mine.
Okay, so K11, any guesses?
Like 12.
No, what was the first term in our stiffness matrix? In your notes?
Oh. The angle muscle number,
Pretty close. Yeah, you've got the 1 plus Nussel number.
Oh.
Yep. So how do you do integration in MATLAB? What's the command? INT. 1 plus NU times x squared, close parenthesis, oops, sorry, I put a parenthesis here before the Nussel number, negative, comma, 0 to 1, close parenthesis, plus 1. Exact term that we have written down in your notes. You're integrating from 0 to 1 with that equation. And now you can kind of copy and paste, right? Because they're very similar, just different numbers. This is 2 times x plus Nussel number raised to the third. And paste that one. This is 3x squared, Nussel number fourth. Hopefully you see a trend. And I didn't give you the rest of these, but I can write them here, so then you can fill them in if you wanted to. Cool. So this is 2, 1, 2, 2, 3. This is 2 times x raised to the third. This is 4. This is 5. This is 4 and 6. This is cubed, cubed. So 2 third, 4 second, 6 fifth, and then down here. I'll wait for you. I got 15 years of typing experience on everybody. This is the trend. If you notice, this is for cubic. If you did quadratic, it'd be a different trend. Linear. That's what I see. Build the K matrix. Semicolon. After the third one.
Oh.
That brings it down to the next month. And while you're trying, if you're updated, try finding the F matrix. If you notice, this is very similar to direct formulation. The coding. You have K, you have F, you invert. And all you're doing is you're doing the differential equation, but you're approximating it by using FEM with a quadratic equation.
It's a 3x1 matrix.
Correct? Yeah. So a little bit of FEM, a little bit of math, a little bit of programming.
A lot of tools.
Yeah. Just like we did. You could do either way, but I like to do F11, F12, or F21, F31. Okay. Nice. People are getting the programming. That's good. That's a plus, right? So this would be K11 space K12 space K13 semicolon. I'll do dot 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 so you can see it easier. I enjoy doing this because it's challenging, but in the end, it makes sense. I hope. In my mind, it made sense. I don't know if in your mind it makes sense. We can do that after. So F11, F21, F31. You don't have to. It should know. If it doesn't work, we'll put them in there. I have them in there in my code, but I don't think it matters. It should know. And once you have, if you notice, I have K1 and F1. They're evals. I'm evaluating those matrices with the X. That's fine. Then see, keep going to solve for the constants in our equation.
Oh.
Some of you never touched MATLAB much for the semester. What's it?
You still have to take it.
How is everybody doing? So you see, I'll leave you here for a few minutes, and I'll do it. See if you can figure out how to now get A, which are the constants for the cubic, and then plug in T star and T hat.
Oh.
We're evaluating those values. Oh, if you run this, guess how big H is.
Oh.
3 by 1, because it's A1, A2, A3, right?
Run. Oh, that's great.
You know how to extrapolate A1 out of A. What I would do is write A1 equals what? Or you could just use A. Now that will know that it's. And then how do you do A2 and A3? Because then you need to write 3 stars. Okay. Oh, you're still working on getting MATLAB working? They do them very. Hey, yeah. Like it. Like it. Dante, you making sense? There you go. Yep. And that's T star though, right? And you gotta find T hat and plot it. Oh, you can't put the star on that. You have to do like underscore S or something. Yep. Okay, Mr. Homer. How are you doing?
Actually, yes. Yep, love the C to the S. Technically, I'm welding the C. Technically, I'm welding the C to the.
You should have left the vibrations that were yesterday.
Actually, the janitor.
I came in and I was like, whoa.
Were you?
Yeah. So I did not take that class. Yeah. It's a good little hunting scenario. The janitor upstairs.
Yeah. He's like, you're not supposed to start over here. Y'all know it.
Plot on the same figure. Yep, and make it like squares.
We're welding the C to the C hinge. C hinge to the S. Technically. But basically, we're welding the C.
Oh, yeah. Yes.
Does that T star, T hat?
Well, is it, I mean, it's T star.
And you star, oh, you'd have to write it out or S.
I just really had a question about what star. Oh,
And once you have the T hat, plot that against on the same graph, using square. Hey, it fifth math.
So are you able to use eval?
Yes, I think you must have to eval again because you have X as a sim. Yes.
Oh.
But you can do that at the end, like, yep. So what did I do? So I did this. So A equals K1 to the minus 1 times F. Then A1 equals A of 1. Oops.
I mean, he can't run it anyway. So he doesn't know that it's wrong.
The T star. What's the matter?
You forgot it's F1 in your
Oh yeah. Thank you.
No.
So K1, negative 1, F1, I did that. A1. So this is T star. And then we have T hat, which is T star plus 5 divided by 3. And then hold on, plot X versus T eval of T hat underscore, let's make it square green ones. And I think that should work.
Oh, no, I suppose it fell. Before I put it.
Well, if that doesn't work, this is what we'll do. Right here, just define X again. There. You could do that. That should work. I don't know if you need the eval. You don't need the eval. Let me know. I'll delete it. I can't run it. Yes. Yep. I made it smaller because it's not the exact. So it should be. No. You can leave that. That's the theoretical, the numerical or FEM approach. Let's see. Where is everybody? Not work?
Doesn't work with the eval.
You need dots? Do I have dots? Oh, that's why. Let's try that.
Give me an error using eval.
Okay, so if we take off the eval, keep the dots. Try that now. That doesn't work, I'll keep. It should work. Thing? So, did he save it? Hey, there you go. Okay, I'll make sure everyone hears it. Is it, did you save this?
Yes.
You all save this.
Yo, hold on, Craig, I got a big thing.
Almost right.
Better?
Dante, can you show yours?
Whoa. Whoa, how did you do that?
Even that, hey, you got it.
How
did you do that?
Yeah.
I meant like, you only needed those 3 parentheses and you got it working. Alright, nope, no dots and no.
A1, 5 seconds. Let's take it.
You go here and type T is correct.
Hold on.
So take the T and the eval off.
Just keep running, it'll.
Maybe it'll give you different numbers.
Yeah.
Oh, right here. X equals. Really?
INT.
On.
Parentheses.
Yep.
Delta
On one.
times parentheses 1 minus 5 thirds parentheses. Comma 0, comma 1.
I don't want to say it. I had that there.
1
But-
minus
You missed something.
parentheses 5 thirds.
It shouldn't look like that. I'll show you what it should look like. You might have missed something. Let me zoom out here, and I'll keep coming around, but I'll make this bigger so you can look at it. And I got to get the graph up. Hold on. So
1, 2x, 2x squared. Squared, 2, 2x, 4x squared, 6x. 2, 4, 6.
oh, not in vibrations.
6x squared, 6x. 9x.
Got to remember where it is.
Oh, do I know? Do I know?
Shoot.
Squared minus 4.
Well, I don't have it, but shoot. Double check to make sure you have those right. But you should get a graph that looks like this. This is like the dotted squares. I'll come back, Ryan. Not work. Okay. Again.
Doc,
Oh, yeah, now it looks better.
Doc.
Yeah.
It's giving me undefined, for INT.
What?
Undefined what?
INT, undefined function.
You don't have Sims? This is your mail app on your computer?
It seems like you took that one. Make your car.
I'm not sure when it gives me an error.
You don't need that.
You follow me up the hill.
Oh, Linux hacks.
Slow it down. Oh, that's really
Because I
You don't need the dot
I
for it.
I wanted to only to one side.
And I just went, whoop, and got right up to it.
And I'm thinking, what, I like racing. And then I sent it up the hill.
And I was like, that's his car.
Yeah, it kind of smells like it doesn't have pads.
Ryan, you good yet? You Ryan?
I think I figured it out.
What was it?
Well, it's still doing the same thing that it was before, but
Nobody thinks that.
at F12, F13, not 21, 31.
But it's still giving you an error?
It's still giving me the same one that I had before. The same graph. Still got one that's down here, and then it's got that one up there.
If you read my Bible.
I think so.
Yeah.
I don't need that one right there. One multiplication. Okay.
Mine's 5
Oh, so.
One thing is wrong somewhere. Oh, your theoretical calculation is wrong. Did you add one at the end?
No.
So, is there a problem with the old?
Get rid of
The funny thing is that she looked at it. She had already done it.
Oh, I want to see her.
Stop. It's still giving me an error.
Okay, almost there. I'll go through this.
I want to see her.
Do I need exit?
Because I want to see what board she wrote and what I wrote. Because Haskins was like, oh, you don't need to like this at all. I basically said, you change this hat and it's important to this. Like, what board?
You have to redefine that.
Stop.
So everyone pretty much has it? Okay, so what you just did there was FEM on a differential equation. You approximated this differential equation as a cubic approximation. What do you think a quadratic or quadratic would look like? So this power of 2. No, it'd actually be worse, right? It'd actually just go like this. What about to the 10th order? It would actually follow that more, right? Up and down. But you see how long a third order was? You'd have to just make this even bigger. Okay? So basically, this gives you the fundamentals. I'm actually going to stop. On Tuesday, I'm going to show you the next step, which you define shape functions. We'll do another code. I'll probably have that code for you. And then that'll be it. Okay? So spend the rest of the time or whatever you need to do to get stuff done. But I think that's enough. So.
Doc, question, can you tell me a real question?
Yep. Let me hit stop.